So now we're going to take a look at the last chapter in Unit 2. We're going to look at how environmental systems and ecosystem ecology work together. So we're going to play. I'm going to turn on my laser pointer. All right. So if we take a look at our objectives today, we're going to talk about environmental systems. We're going to look at the interaction of living and non-living parts of the system. We're going to talk a little bit about modeling, because that's a really important part of our understanding of how environmental systems interact. We're going to go back to ecosystem services again, because they're super important. We're not going to do a whole lot of this comparing the biogeochemical cycles, because I've got an activity that we're going to do that's really going to solidify that for you. They're important, but there's a better way of going over those things. But we are going to talk about how human activities are impacting these biogeochemical cycles. So let's get started. The case study for this chapter deals with Chesapeake Bay. Chesapeake Bay historically has been one of the most prolific oyster harvesting areas. Oysters were really prevalent in the Chesapeake Bay, 150, 200 years ago, but there's been a collapse in oysters. Oysters are benthic, which means they're bottom dwelling, and they're sessile, which means they don't move. So oyster larvae, yes, they're sexually reproducing organisms, so they produce larvae. The larvae will settle out of the water column and wind up landing on something and cementing themselves to something hard on the bottom. So this is our first conversation about watershed. A watershed is an area of land that sheds water into a bigger body of water, okay? So the watershed, we're going to see it on the next slide, delivers nutrients that kept these underwater sea-ish grasses, that's kind of brackish water, these underwater grasses alive, okay? Because like the plants that you grow on your porch or in your garden, they need nutrients. So the watershed, the water that ran off the land, provided those nutrients. The cool thing about it was those grasses provided a habitat for fish and shellfish, and the oysters helped, contributed to their ecosystem by filtering nutrients and phytoplankton out of the water. So by 2010, the oyster population was down 99%. Now, a lot of people say, oh, that's got to be overharvesting, but it's more than overharvesting. It has to do with too many nutrients that make their way into the bay through fertilizers, manure, and fossil fuels. So the fertilizers and manure make their way from the surface down into the water. Fossil fuel combustion produces nitrogen gases that will then fall as the result of combination with water in the atmosphere into the body of water. And we're going to talk about how that happened. You lose oysters in overharvesting, but there's another thing that happens. It's this idea of hypoxia. These nutrients caused a bloom, an algal bloom, too many phytoplankton, and then they died. They fell to the bottom, and bacteria decomposed them. Bacterial decomposition uses up oxygen, and it created a low or no oxygen zone. They call that hypoxia if it's low oxygen, or anoxia if it's no oxygen, okay? And every living thing, plant or animal, needs oxygen in order to survive. So there's a dead zone that's there. So they didn't do a really good job protecting the bay. There are some indicators that the bay is coming back. You can look at these levels, okay, over the last, 40 some odd years, okay, 30 some odd years. So it's starting to get better. Okay, so let's look at all of the parts, all of the moving parts in this case study. So if we look at a system in the grand scheme of the universe is a network of relationships that influence each other. Okay, so systems thinking, when you think about that, is looking at ways that different elements in a company or in a school influence each other, how information flows, how materials flow, that kind of thing. So the Chesapeake Bay gets inputs. Okay, they get fresh water, sediment, nutrients, all things that we need, and pollution from the watershed, the area of land around Chesapeake Bay. And fishermen get some of the output, typically matter and energy in the form of seafood. So if we take a look at the boundaries of systems, okay, just from an Earth perspective, there are 4 main Earth systems, 5 if you count the one we're going to talk about. The lithosphere is the rock part. The atmosphere is the air. The hydrosphere is the liquid water. You can also throw the cryosphere in there, which is the frozen water. And then there's the biosphere, which is all the living things. But something that makes it hard to delineate, right? There's water, hydrosphere, mixed within the lithosphere. If you have a well, your well is tapped and drilled into the earth, into the lithosphere, and there's water down there. So there's hydrosphere within the lithosphere. When we get to the last unit and we start to talk about soil, a key thing that needs to stay in soil is air. So the roots have air and don't drown. So there's atmosphere within the lithosphere. All right. There's atmosphere and hydrosphere within the biosphere. There's air in our lungs and water in our bodies. Okay. So we can't really draw hard lines where one starts and the other stops. The interactions in between the atmosphere and the hydrosphere, between the atmosphere, the air above the ocean, and the ocean itself is a really big thing that we're going to talk a lot about as we get further along in the course that relates to climate change. Okay, so it's really hard to draw a solid line. So how these spheres interact helps us understand ecology. This is huge. This is a big idea in this course that we're going to keep coming back to, especially when we get to the section on climate change. So you can look at the input in a system and the output in a system, and you get something called a feedback loop. Okay? So a negative feedback loop comes when a system moves in one direction, right? When a process has happened to allow the system to do what it does, and it pushes it in one direction, what comes out balances it, okay? So when you hear the word negative, you think bad. A negative feedback loop is a good thing. A negative feedback loop balances a system, keeps the ups and the downs level, okay? And this is one in your body. So if you are too hot, okay, your brain gets the signal that it's too hot. So when the brain gets the signal that it's too hot, that forces you to either sweat to cool down or to get into the air conditioning, to take a cool shower, seek shade, do something to cool your body down. Your body then winds up cooling down, right? So it balances. The negative feedback loop, your body's reaction balances the system, okay? But sometimes you get too cool, okay? If your body gets too cold, that tells your brain that you're too cold. You throw on a blanket, you put on a sweatshirt, you start to shiver, right? You start running around, rubbing your hands together, anything to raise your body temperature. So then your body warms up, okay? So what goes in balances, right? It's a balancing thing. A positive feedback loop is not a good thing. A positive feedback loop is where what comes out rolls back in to the system, which then creates more output, which then creates more input, okay? So this is a classic example of a positive feedback loop. In my head, what I see when I hear about positive feedback loops, If you watch the old like Bugs Bunny, Tom and Jerry cartoons, they've got a little pebble sitting on top of a mountain, like a snow-covered mountain. And whoever is at the top, whether it's the good guy or the bad guy, he or she flicks the pebble and it starts to roll down the hill. And as it starts to roll down the hill, it picks up all of this snow. So the further it rolls down the hill, the more snow it picks up. So that's a positive feedback loop. It's definitely not the kind of outcome you want. All right. So if you look at a real world example of a positive feedback loop rather than a cartoon example, melting glaciers and sea ice in the Arctic is a really good example. So in a cooler climate, right, like when it's covered with snow, the surfaces, the snowy surfaces reflect a lot of sunlight, right? It's called albedo, which we'll talk about. When that sunlight gets reflected, the air stays cooler. Okay, so the air winds up staying cooler. So the land stays cooler, so the ice gets to stay. As the climate warms, as temperatures on the earth start to warm, some of this ice melts, okay, exposing dark surfaces. Dark surfaces, as you guys know, absorb heat, right? That's why you don't wear a black shirt in the middle of summer. You wear lighter colors to reflect that light and that heat, okay? But as the ice starts to melt, dark spots are exposed, both on the land and in the water. So what winds up happening is that that sunlight, that radiation, is absorbed by the surface, right? It's going to be absorbed more by the dark surfaces than the warm surfaces. So that's going to warm up the dark surfaces, which is then going to increase melting, which is then going to increase the area of dark land and water that is exposed, which is going to increase melting. So that's the positive feedback loop. It's this cycle that winds up making a situation worse and worse. Okay. Negative feedback systems help equilibrium. They help keep everything in homeostasis, in balance, right? Homeostasis is same status is what it literally translates from. Stable internal conditions, right? So when you have a fever, your body temperature is out of homeostasis. So you have feedback loops in your body to balance that out. The earth has the same kinds of feedback loops, and we're going to talk about lots of them as we get further through in the course. But it's a really important concept to understand. Okay? We know that the systems are not isolated. They intertwangle. So this is a really important concept. It's this idea of runoff, okay? We have Captain Obvious statements in every lecture. Here's one. Runoff is water, precipitation that falls on the land and literally runs off. It flows over land into waterways and eventually making its way into the bay in this case, or the creeks and streams down into the Delaware River around us when it rains a lot. So it includes the watershed and the airshed. So this green here is the entire watershed of Chesapeake Bay. It goes from like central New York all the way down into central Virginia. It's a huge area of land that drains into Chesapeake Bay. And if you look at what's around there, you got farms, right? So there's where your agriculture comes from. The eastern shore of Maryland and Delaware is full of chicken farms. So chickens poop, they produce manure that washes off and makes its way into Chesapeake Bay. Cities, Washington, D.C., Baltimore, Harrisburg, Richmond, Norfolk, they produce a lot of, they burn fossil fuels in the cars and in the factories, so then that winds up making its way into the water. Industry, the same thing. And there are also lots of forests here too, to kind of help balance everything out. Most of the nitrogen and phosphorus pollution comes from agriculture, right? This is nitrogen and this is phosphorus, but quite a bit comes from, in terms of the nitrogen, comes from the atmosphere, okay? Fertilizer, right? When you fertilize your lawn, or you fertilize flowers and you don't do it carefully, a lot of that is going to run off into the watershed. Okay, so let's tell this story. It's like the next 3 slides, 2 slides, whatever. But instead of going through it from one slide to the next, I'm going to tell you guys the story here. This is a really important story for you to understand, because this is a key concept when it comes to systems ecology. All right, so here's the freshwater river, right? All the water that runs off into Chesapeake Bay. This is Chesapeake Bay, a model of Chesapeake Bay. So the water runs off, right, and brings lots of nitrogen and lots of phosphorus. Nitrogen and phosphorus is essentially fertilizer. It's what you guys wind up using on your plants when you grow them in your garden, or the flowers, or whatever you do, okay? So that's going to take the phytoplankton, which are the plant plankton, and it's going to cause them to bloom. They're going to reproduce, right? They're happy little phytoplankton, so they're going to do their thing. They flourish at the surface, right? Phytoplankton have a lifespan. Eventually, they're going to die. They're going to die, and they're going to fall down to the bottom, okay? And they're going to start to decompose. Decomposition uses cellular respiration, requirement of cellular respiration is oxygen. So these phytoplankton are going to fall to the bottom and are going to start to decompose, right? So these bacteria that are going to do the decomposition, these little guys right here, are going to suck up all the oxygen. They're doing so much decomposition, producing, sucking in that oxygen and turning that material back into nutrients, okay? So they are going to deplete all of that oxygen, right? We talked about this at the beginning. Every living thing needs oxygen. So you're going to wind up with this dead zone where nothing lives there. It's a hypoxic zone or an anoxic zone if there's absolutely no oxygen, okay? So anything that lives down here is going to be dead. The previous slide, 2 slides, yeah, it shows you right here. Okay, healthy waters south by Norfolk are going to have quite a bit, 10 milligrams per liter of oxygen. Dead zones from Baltimore south, almost to Richmond, have almost no oxygen, okay? So you can see the impact that this process is having, okay? So we talked about that, increasing decomposition. What this is called is eutrophication, a huge important concept. You're going to see it again and again, right? This process is called eutrophication, as the waters become hypoxic or anoxic, okay? The bacteria completely suck up the oxygen and nothing survives. All right, definition of an ecosystem is the living and the non-living components in an area, okay? If you look at a community, it's just the living organisms. If you throw in those abiotic or non-living factors, you get an ecosystem, all right? And the system in Chesapeake Bay is completely impacted by all of those factors that exist in the ecosystem. Okay, another super important concept. We talked about in the last lecture, we talked about consumption, right? And food chains and food webs, okay? That is the flow of energy. So energy moves, okay, from one organism to the next through the consumption, right? So the energy from the plant goes to the grasshopper, the energy from the grasshopper goes to the chipmunk or rodent, and the energy from the rodent goes to the hawk. Remember, only 10% of that energy gets from one trophic level to the next. So don't be surprised if you see questions related to the math for that. As energy flows, right, some of that energy can't break the laws of thermodynamics. So the energy doesn't disappear, okay? It gets lost. It gets converted into non-usable energy. Typically, mostly is heat, right? So energy flows in one direction, from producers up, right? So that's super important to understand. Matter, however, does not. Okay? If you notice, this heat goes off in one direction. Matter, okay, winds up cycling. So the plant gets eaten by the grasshopper, the energy goes in that direction, and the energy keeps flowing. However, okay, everything is going to die, right? So this matter, these nutrients and molecules that each of these organisms are made up of, once they die, they get decomposed, right, and broken down thanks to detritivores and decomposers. And then those nutrients make their way back right here with this little gray arrow back to the plants to come through. So we're following the gray arrows here. Okay, everything comes back in the gray arrows to the plant. So energy flows in one direction, matter cycles. And we're going to talk about those cycles briefly in a little bit. Okay, so when we talk about this process, okay, of energy flow, okay, the conversion that process that producers do, right, when they take solar energy and turn it into chemical bonds is called primary production. All right. If you look at the total chemical energy that all the autotrophs in an area create, they call that gross primary production. Okay. So all of the photosynthesis and chemosynthesis that organisms do, put it all together and you get gross primary production. All right. Plants and animals need to use, plants in particular in this case, need to use some of that energy for to generate their biomass, to grow, to reproduce, etc. After they use respiration, what's left is called net primary productivity. So what we're going to do some math using the formula NPP, net primary productivity, equals gross primary productivity minus respiration. Okay, so the overall term for the rate at which energy is converted to biomass through photosynthesis or chemosynthesis is called productivity. But this math is like really easy, I promise. Different ecosystems have different amounts of productivity. Okay, so your terrestrial ecosystems are the green, your aquatic ecosystems are the blue. Algal beds and coral reefs tend to be some of the most productive ecosystems, aquatic. Tropical rainforest, this shouldn't be a surprise to you guys either, that the tropical rainforest, based on all of the studying you did in elementary and middle school, is the most productive terrestrial ecosystem. Okay, you get down here to deserts and the tundra, they're not very productive, right? And that kind of makes sense too. In the open ocean, this surprises a lot of people. There's not a lot of productivity in the open ocean. Okay, so that's going to come in really handy for you guys, this diagram. I'd star this or pay attention to this somehow for future reference. This makes sense too, okay? The higher the temperature and precipitation, the greater the productivity on the land, okay? And it kind of makes sense. And areas that have greater nutrients and greater sunlight tend to also have higher productivity in the water. So the open oceans have a lot of sunlight, but they don't have a lot of nutrients. So that's why they're not that productive. You need land in order to get greater productivity. So I've been bantering this word around, nutrients. So nutrients are elements and compounds that are really essential for organisms' survival. Okay, they're things that we need in larger amounts. They're called macronutrients. Some examples are nitrogen, carbon, and phosphorus. And then there are nutrients that we need in smaller amounts. Those are called micronutrients. Zinc, copper, and iron are some examples. If we look at limiting nutrients, right? Nutrients that restrict the type and the amount of life that exists in an area, Nitrogen tends to be that limiting nutrient in marine or oceanic ecosystems, okay? Phosphorus tends to be the limiting factor in freshwater systems, right? So phosphorus, if you put phosphorus in this lake, they walled it off, isolated the circulation, you wind up getting an algal bloom, okay? Kind of like what you saw in Chesapeake Bay. We talked about the dead zones, right? Typically you get these more dead zones, these dots, where you have a greater human ecological footprint, where there's a greater amount of human influence, okay? So there's a lot off the East Coast and the Gulf of Mexico in the United States. There's a lot in Europe because there's a huge ecological footprint, okay? So that's kind of makes sense. So there are areas, and you guys are going to talk about, we've already actually talked about biomes. So there are areas where the biomes intertwangle, right? It's not like there's a solid line between the tundra and the boreal forest or the taiga, right? There are areas where they kind of overlap. Those overlapping or transitional areas are called ecotones. And organisms that live in these ecotones face unique challenges, right? So you've got these little patches of grassland in the forest and the patches of forest in the grassland. If you're an organism that lives in this little tiny patch, you know, your resources are going to be a lot more limited. So you kind of have to do with what's around you or be able to get, you know, somewhere else where you've got the right kind of environment for your resources. So we're going to talk briefly about this because everything is so complicated. We use models a lot in environmental science to look at how different pieces of that system are going to interact and to try and predict it. It's difficult. It's very difficult to make those predictions. So you take a look at relationships. You design a hypothesis to explain the relationship. You make a model to predict it. And then you see if it works or it doesn't. And it's just another feedback loop to try and figure out how things work. So it's a challenge. Ecosystem services. We've talked about them. And we're talking about them again. Normal ecological processes that are the result of healthy ecosystems do really amazing things for us. They form soil, they purify water. We talked about pollination, okay? It's the breakdown of waste that's able to be broken down, like the dead deer on the side of the road. And ecosystem services are a system of checks and balances to keep those negative feedback cycles in balance, to prevent them from becoming positive feedback cycles. All right. Some of the most important ecosystem services, right, are related to elemental cycling through biogeochemical cycles. All right. Biogeochemical, let's break that word down. Bio is life, right? Geo is earth, and chemical is nutrients, right? So it's the cycling or movement of nutrients through living things and the earth, okay? They travel through those earth systems that we talked about before, all right? So that's a biogeochemical cycle or a nutrient cycle, all right? So different nutrients can stay in areas for different amounts of time, okay? So we are reservoirs for carbon, right? It's a pool. It's like a holding tank for this particular nutrient. So residence time is how long a nutrient is in a particular source, reservoir, all right? When it releases more material than it accepts, that reservoir is called a source. If it accepts more than it releases, it's called a sink, okay? So we're going to talk about sources and sinks. Flux is how fast materials move between reservoirs. But the idea of a source and a sink is important. So these are the cycles, right? I'm not going to dwell on them here, like I said, because you guys are going to have an activity where you deal with them. But the water cycle is important. There's a picture of the water cycle, and the arrows show the movement, and the numbers show how much moves or how much is in a particular area. All right, one thing that they like to talk about a lot is transpiration, which is the equivalent in my mind of plant sweat, right? It's what the plants lose through their leaves. Precipitation. If you guys have a well, you have groundwater, right? So your well is down into this aquifer. So how are we messing with the water cycle? So we're damming rivers. So we are slowing down the progress of these rivers to generate hydroelectric power. And we're putting all of this water in one spot, so we're increasing evaporation. When we remove vegetation, right, when we clear for farming and whatnot, it increases runoff. So the water doesn't get a chance to soak back into the ground to recharge aquifers. All right, we are pulling water out of the ground faster than it's going back in. So we're lowering the water table, and we're going to talk a lot down the line about air pollution and how that's changing the chemical nature of precipitation. The carbon cycle, right? This is a pretty complicated cycle. There's a lot going on here. There's carbon in the ocean. There's carbon in the atmosphere. There's carbon underground in the form of fossil fuels for the most part. Okay, so we talked about how producers pull carbon out and convert it into glucose. Carbon frequently, as you have these aquatic organisms die, they settle to the bottom of bodies of water and get converted into carbonate or carbon-based rock, okay? So you need to know that sedimentary rock is the largest reservoir in the carbon cycle, right? So once those critters die and plate tectonics takes over, they get subducted, and carbon is put back into the geosphere. There's also a lot of carbon that's held in the oceans. We're going to talk about that in the future. We are shifting the carbon cycle, okay? We are messing with the carbon cycle. This is really important for you to understand, okay? We are pulling carbon in the form of fossil fuels out of the lithosphere and putting it into the atmosphere faster than it's being returned into the lithosphere, okay? So we're burning fossil fuels, and we're also decreasing surface vegetation. As we decrease surface vegetation, it's like chopping the lungs out of the planet. There's no place for the carbon dioxide that we're putting into the atmosphere to come back, okay? So we're definitely shifting the carbon cycle, and it's causing the oceans to become more acidic. We are definitely going to talk about ocean acidification down the line. The nitrogen cycle. The College Board loves the nitrogen cycle. And there it is. Okay, nitrogen fixation, combustion, there's a lot going on here. All right. So nitrogen fixation is where you have atmospheric nitrogen becoming biologically useful. Okay, bacteria typically do that. And it can also happen as a result of lightning strikes, which is kind of cool. Okay, they're found in the root nodules of legumes such as soybeans. Okay, so farmers will leave soybean stalks in their field to increase the nitrogen content in their soil. Okay, more about that process. And there's a cute little picture of a different picture of the nitrogen cycle. No, that is the picture of the nitrogen cycle. So you've got denitrifying, nitrifying, ammonification. There's a lot going on. We have done a lot to influence the nitrogen cycle. You can they've developed this process that you're not going to get tested on, to create nitrogen to make fertilizer. It's called the Haber-Bosch process. But that's also caused issues, right? So if you have enough nitrogen fixation to create fertilizers and stuff, you're going to cause eutrophication because you've got too much nitrogen running off from not careful fertilizer use. And then burning fossil fuels releases nitrogen into the atmosphere, which then combines with water and falls onto the land. Phosphorus, okay, there's not a whole lot of phosphorus in the atmosphere. So most of our phosphorus is terrestrial. There's very little atmospheric component to the phosphorus cycle. Teeny tiny in comparison. Okay, most transport of dust and sea spray in the atmosphere, 1 versus 4 billion in the sediments and the sedimentary rock. Okay, and that's how that happens. We are increasing phosphorus in the ocean as the result, and in the water as the result of using detergent and dish soap. They're high in phosphorus, so that increases phosphorus concentrations in the waters. So what can we do? How can we reduce the nutrient pollution that causes eutrophication? This is the first time you guys are hearing this. This is definitely not going to be the last time. So how can you do it? You can be more judicious with your fertilizer application, right? Whether you are a homeowner in a residential situation or if you're a farmer. Instead of fertilizing, like you do every year, test the soil, figure it out, see if you really do need the fertilizer, and be careful with your fertilizer application. Keep cover crop planted. Okay, this is cover crop. This is cover crop, to prevent soil erosion and soil loss. You can plant a vegetation buffer, right? So they plant trees a lot of times around wetlands to prevent those nutrients from running off of farm fields and in residential areas into water. Sewage treatment is another big thing. Wastewater treatment plants, as you're going to find out eventually, if they're not running well, some of that wastewater material, which is essentially fertilizer, it's manure, just human manure, is going to make its way into local bodies of water if it's not functioning well. Okay, so making sure that it's functioning well is really important. And reducing fossil fuel consumption, preventing those nitrogen compounds from getting into the atmosphere and then making their way into the water. If you look at the cost, right? So it's going to be really expensive to get nitrogen out of stormwater in general, okay? It's really expensive. The cheapest thing to do is to do like the easy things, and they're the most effective, okay? So reconstructing wetlands and using cover crops rather than completely upgrading the wastewater treatment plants, okay? So now we've kind of talked a little bit about systems, and we will now be at the end of Unit 2.